Right, this problem builds on the last set of problems we saw where we studied the acceleration of a mass that is away from the center and how that affects. This time we're looking at an object A, B, C. It consists of two slender rods welded together at point B. Rod AB has a weight of 2 pounds, and bar BC has a weight of 4 pounds. Knowing the magnitude of the angular velocity of ABC is going to be equal to 10 radians per second when theta equals 0. So theta is going to be 0. So we are going to be up and down here. See, if we're drawing our free body diagram, it's going to look something like this. A, B, and C, and we'll have forces CY and CX. Determine the components of the reaction at point C at this location. So we're trying to figure out how strong do we have to make this for it to hold up under this weight and move at this angular velocity. All right. Where should we start? One of the things that we're going to need to know will be the mass moment of inertia. So we could start off calculating the I bar for section AB, which is going to be 1/12 the mass times the length squared. That means we're 1/12 multiplied by 2 pounds divided by 32.2 to get it into a mass. And we are 1 foot. And that's squared. So the I bar for AB is going to be equal to a small number, 5.1760 times 10 to the minus third, and slug times feet squared. What about the I bar for section CB or BC? Either way, we're going to have 1/12 multiplied by the mass of that bar and multiplied by the length squared. And that's going to be a little bit bigger because it's a little bit bigger of a bar. Slug foot squared. Now let's focus on our free body diagram here. We've got what we need to find. We listed. We also know that there's going to be weight for BC. There's going to be a weight for AB. And we're going to have an angular velocity. And since they show theta growing in this direction, I am going to put my omega in the plus direction at 10 radians per second. And then I'm going to look at the dynamics part of the problem. We've got all of our forces listed. We're going to have a center of gravity here, which I'm going to label E, and I'm going to label this DE, A, B, C, D, E. And we're going to have a normal component for the acceleration at E, and we're going to have a tangential component of the acceleration at E. We're going to have a normal, we're swinging around C. So if we do our best to draw a arrow for the normal. I know wrote over my E, but oh well. The normal component is always directed to the center. And the tangential is going to be at an angle of 90 degrees from the normal. So we have that set up. It would be helpful to figure out the lengths of my C with respect to E and my C with respect to D. If I do that, I'm going to have R of C with respect to D, and I can just do a Pythagorean type of theorem here, where I am going to have a right angle right here. So I'm pulling out a triangle that looks like this. C, D, B. B. And this leg is going to be 0.5. This component is going to be 2. And I don't know what this is. That's what I'm looking to find. I only know this angle. I don't know this angle. I don't know this angle. So let's see what we can do here. We can do the Pythagorean theorem to find the hypotenuse. That's going to be 2 squared plus 0.5 squared. And so you're going to have R of C relative to D equal to 2.0616 feet. And we could do this in a vector format, but I think we'll practice a scalar format. We're probably ready for that. And we'll keep with that value for this distance of the hypotenuse. Then I need to figure out what R of C relative to E is going to be. And so that's simply going to be half of the length of CB. So R C to E, this is where I made E, we're going to have 2 divided by 2, which is going to give us 1 foot. Okay. Now, in terms of figuring out what we need to know at C, we're going to need to find all the things related to alpha of BC, alpha AB. We're going to look at needing to know what our tangential and our normal components are equal to. So we're going to find the acceleration at the center of mass for E and the acceleration of the center of mass at D. And if we are able to find all of those acceleration components, we will be able to sum forces and build an equation to solve for what Cy and Cx is. Okay. I'm going to start off by wanting to sum moments around C. And so that is going to be equal to I bar alpha plus MAD. And this time we have 2 different pieces that we need to worry about. So when we're summing moments around C, we're going to have the I bar for piece AB times alpha AB plus the mass of AB, which was given to us. We were given pounds, so we'll have to turn that into slugs. So we'll have to work on that. And our acceleration, again, this is going to be like the problem we had before, which is going to be that acceleration in the tangential direction, which is equal to r alpha. And so we're going to need the r value we just found for, let's see, we're on this one, so we'll need CD. We'll need the tangential component, which is going to be another r of CD multiplied by alpha AB. And then we're going to look at this piece. So added to that, we're going to have I bar of BC times alpha. Now, can this in any way have a different alpha if they're a rigid body connected? There is no pin connection here. This is not broken apart. So we're really going to move as a unit. And therefore, in this problem, we really only have one alpha. AB plus mass of BC times R of C relative to E. And then the tangential component as well. Both of the normal components go through C. So let's have R of C relative to E multiplied by alpha AB again. And that should take care of all of the components we need to be able to calculate our alpha. We know mass, that's been given to us. We just found out our R components. We found out our I bars, and we can sum moments on the left-hand side of the equation with our forces. All right, so on the left-hand side of the equation, if we're summing moments at C, and we're thinking back to statics, so we don't worry about anything in red, the only thing that creates a moment around C is the weight AB. And that is going to be equal to 2 pounds. And it is going to be at a distance away from C. That is right here. That's going to be half of 1, which is 0.5. So we are doing a cross product right here. C to the line of action for the weight. That is 0.5 multiplied by omega, or weight AB, and that's 2. That's the only thing that relates to the statics part of the problem. Now let's plug in the whole right side of the equation. AB is the 5.176 times 10 to the minus 3 times alpha AB plus the mass of AB. So that's going to be 2 divided by 32.2 to get it into slugs, multiplied by CD, which we calculated to be 2.0616. And if we multiply that out, we're really squaring it. And then alpha AB. We've taken care of the bottom piece. Now we're adding to that. Let's start another row. The BC, 41.5 408 times 10 to the minus third. Looks like I messed up there. 10 to the minus third. There we go. And we're going to multiply that by the same alpha. Plus, we have a different weight, 4 pounds, divided by 32.2, multiplied by CE, which is 1, and it is squared, multiplied by AB. Okay. So if we solve this, we should find that alpha, what we called AB, which is alpha for the whole system, is 2.3 radians per second squared. And since we are going counterclockwise, we are going to call that a counterclockwise positive K direction. All right, now to move on to the portion of summing forces in the X and the Y direction. Summing forces in the X direction equals mass times the acceleration in the X direction. If we look at our free body diagram, we have two weights going down, but the only force we have is Cx in the X direction. And we labeled that as a plus component, so I'm going to put it in to match my free body diagram. I'm going to have the mass of AB multiplied by the component in the X direction. So I am looking at AB multiplied by this, but I only want the X component. So I want AT in the X direction for AB, rod AB. That's what I'm looking at. And that's going to be equal to the acceleration of AB. That's tangential. And how do I get the X component for that? If I want the X component for this direction here, I am going to have to find one of these angles, either this one or this one to work with. So let's work on finding out the angle. This one, I would be able to say the tangent of theta is equal to opposite over adjacent. And I guess theta isn't the best thing to call this because we don't want to have two thetas. This theta is not this theta. So let's call this phi. All right. And if we work that out, we'll find that phi is equal to 14.036 degrees. Now, we look at our geometry, and we know that we have a right angle to that normal component. This is the AT. And we only want this component right here. And eventually, we can look at, okay, if I know that this is a right angle, and this is part of the triangle here, and that's a right angle, then we can subtract and see that this angle below is going to be equal to this one, B. So I'm going to want to have the cosine component of phi if I'm breaking the tangential component into its x and its y coordinates. Okay. Well, let's multiply that acceleration in the tangential direction by the cosine of phi. Now, what else goes on this side of the equation? What other things do we need to worry about? Does the normal acceleration have any x component? Yes, it does. It is going to have an x component and a y component. So it's going to the right. It's going to be positive. And so let's work on the mass of AB multiplied by the acceleration of AB in the normal direction. And if we want that normal component, we're looking at the sine of phi. So sine of the angle phi. Okay, that takes care of one piece of the link. Now let's look at BC. We're going to have the mass of section BC, and we're going to look at the two acceleration components that, when added together, they are going to be the acceleration of the center of mass. So AE is really equal to A, this is what I called E. So that is going to be the BC tangential plus acceleration of BC normal. And AD is equal to the acceleration of AB tangential plus acceleration of AB normal. Now we're going to have a component for BC. And is that going to create a moment around the point C? The normal component goes straight through C. So only the tangential component will create a moment around C. And so we're going to need to focus in on the acceleration of BC in the tangential direction. That is everything. Or no, we're summing moments in the x direction. We're not summing moments, we're summing forces in the x direction. So AN has no x component. It's all in the vertical. I already did the moment portion. Okay, so let's put in some values. Mass of AB, 2 divided by 32.2 multiplied by, what did we say AB tangential was going to be equal to? That was equal to our R component, which is going to be the R of C relative to D component of 2.0616. So R times alpha. And so that R is 2.0616 times alpha. And we figured out what our alpha is. So we're going to plug that into there. And so the tangential component of acceleration is going to be equal to r times alpha, 2.0616, multiplied by alpha, and alpha we found to be 2.3, and then we're going to do the cosine of phi, cosine, because we only want the x components, of 14.036 degrees. So we've got this portion done. Now let's look at the normal component. What do we do there? We are going to have plus the same mass, 2 divided by 32.2. And we know that our normal component of AB in the normal direction is going to be R of C to D again, so that CD distance, we're still at that R component, and we're going to have omega squared. Oh, so now we've got an omega term to figure out. What are we going to do with that? Let's put it into our equation, and we're going to have R 2.0616 and omega squared AB. Were we given information on omega? Yes, we have omega. Let's put omega into our problem. 10 radians per second, and that's going to be squared. And again, this is more of a scalar approach, so I haven't been putting in all the i's and j's and k's and doing the cross products. Let's see. And so we've got our normal component there, and then sine of 14.03 degrees, 0.036 degrees. Now we just have to deal with the tangential acceleration for the segment BC. So add that in. Mass of BC is going to be equal to 4 divided by 32.2. And we have our tangential component, so we have a different R component. We're going to want this distance right here, which is going to be 1. So 1 multiplied by our alpha, and our alpha was 2.3. And we didn't have to multiply by any sine or cosine because all of that component is going in the x direction. So we have no unknowns in this entire equation. We are able to solve for CX, and CX is going to be 3.6770 pounds. Let's look at summing the forces in the y direction equals mass times the acceleration in the y direction. If we look at our free body diagram that's pretty messed up now, we have 2 weight components going down and 1 CY holding it all up. So the static side, we've got a plus CY, we've got a minus weight for AB, and a minus weight for BC. And that's going to be equal to the mass of AB. And now we have to find all of the components for the acceleration, and we have to get them in the y direction. So that was a cosine of phi. This is going to be the sine of phi. We're going to add to that the mass AB, and we're going to have the normal component of the acceleration in the normal direction. So now I'm looking at this component right here for the red acceleration in the normal direction. I already added in this one. So that's going to be the opposite. It's going to be equal to the cosine of phi. And then let's look at our accelerations for BC. And all of the tangential was in the x direction, and all of the normal is in the y direction this time. So let's add on the mass of BC, and that's going to be multiplied by the normal component of BC. And that would sum up all of our accelerations that take place in the y direction. Let's plug in some numbers and solve for cy. Cy is going to be equal to -4 and -2 for the weights. And then if we're looking at our mass AB, we start to think about the direction this is going. AB in the tangential direction had a negative component. It was going down and to the right. All of the components were plus for our x components. But we have one that's negative and two that are positive for our y components. So we're going to have a minus mass over 32.2 times our distance to get our value for our tangential acceleration times our alpha, 2.3. So that's our tangential acceleration. And since I'm doing a scalar approach, I'm putting the minus sign out front. And I need to get only the y component. So we said that was going to be the sine of 14.036 degrees. So that is this part. Now let's do the right side over here. The normal component in the y direction for AB is going to be positive. It's still going to have the same mass, 32.2. And we're going to calculate what do we need for a normal component. We have the same R value, 2.0616. And we're going to have our angular velocity squared. So that's our AN. And we're multiplying by the cosine of phi. Cosine of 14.036 degrees. And now let's do the last one. Plus, we have a different weight, 4 divided by 32.2 to get it into mass. And we have our acceleration in a normal direction. And we've got a different R component. So this is farther away from C than E is. D is farther away from C than E. So E is going to have a smaller normal acceleration component. And that R is going to be 1. And the omega is the same. And then there is no angle because all of the normal component is going in the y direction. All right, so we've set up the equation. We can solve for Cy. Cy is going to be 30.773 pounds. And both of those are going to be positive. So if we were to draw our free body diagram, once we look at what we have, we're going to have the Cy going up at 30.773 and the Cx to the right at 3.6770. And both of those are in units of pounds. Cx. All right, so that would be our answer for this problem.